In this video, we discuss equation or equalities when things are equal, and inequalities and a complementary notion when things are not equal. Often, we are trying to isolate, evaluate, or estimate some unknown quantity typically denoted by x. Each turns out that essentially the same algebraic tools apply for both equalities and inequalities, though a little bit more care is needed for inequalities. Let's begin with a simple equation involving an unknown x. 2x plus 1 is equal to 7. And as usual, x is an unknown and we want to find out what it is. The idea is that you try and isolate x. So x is embedded in this expression 2x plus 1. We want to somehow separate it out so that we get it standing on its own. Okay, so we just get x in two steps. We'll take one way from both sides and we get 2x is equal to 6. Then we divide by 2 and we end up with x is equal to 3. Of course, when you do a calculation like this, you can always check that answer works, right? 2 times 3 plus 1 is equal to 6 plus 1, which is equal to 7. So left hand side and the right hand side of the original equation agree when x is equal to 3. Again, now let's make things a little bit more elaborate. Again, I'm going to write down an equation, but x will appear more than once. In fact, x appears 3 times and is sort of mixed up in with fraction. Again, the aim is to isolate x. So we'll start off by simplifying the fraction, the expression involving fractions on the right hand side by getting a common denominator of 10, and then the numerator simplify the 7x minus 9, and then we multiply both sides by 10, and then multiply both sides by 2. Add 18 to both sides, subtract 5x from both sides, and we get 18 is equal to 9x. Divide through by 9 and then put x first, and we get x is equal to 2. That was really long process, but you can see that in a principle, it was no more difficult than previous exercise. There is a little bit more rearranging and x appear more than once. Of course, you can check that the answer is correct by feeding back into the original equation and checking that the left-hand side and the right-hand side are in fact equal. But what I want to do next is something that's qualitatively quite different. Let's consider the following equation. Again, x appears more than once. It appears twice. This equation is very special because 0 appears on the right-hand side. The left-hand side is a product of two numbers, x minus 1 and x minus 2. Whenever you have a factorization of 0, you are able to make progress almost immediately. A consequence of this equation is that at least one of the factors has to be equal to 0. And why is that? Well, that's a property of multiplication on a real number. If I take a rectangle side length A and B, then the result of multiplying A and B, which we call AB, geometrically is the area of the rectangle. Okay, now let's suppose the product of A and B is equal to 0. What does that imply about the geometry of the rectangle? That means the area has to be 0. So how can that be the case? It means the rectangle becomes infinitely thin. There's at least two possible ways. The rectangle could become infinitely thin of length b, so a turns out to be 0. Another possibility is that the area could become zero by becoming an infinitely thin line of length A. And now B has become equal to zero because it is in fact the third possibility, and that's the whole thing contracts to a single point with zero area, in which case both A and B are equal to zero. But the upshot of this is that if A, B is equal to zero, if the area of the rectangle is equal to zero, then either A is equal to 0 or B is equal to 0. It is the fact that was used if we go back to the equation to deduce that either x minus 1 is equal to 0 or x minus 2 is equal to 0, where x minus 1 has the role of A and x minus 2 the role of B. So what we have in that original equation is split up into two equations where in each case x appears only once. So by simple rearrangement of the information in each case, we isolate x as either 1 or 2. I would like to revisit this equation using a technique that I saw a student use years ago, and then the student had very little mathematical experience and background, so he was using his own ingenuity, and he ignored this property of zero that we used just now to solve this equation. He just started off by expanding the left-hand side. Okay, so if you multiply out the brackets, you get x squared minus 3x plus 2 is equal to 0. His idea was to again try to isolate x, and the first step will be perhaps to strip away the 2 from left hand side, take it away, and you get x squared minus 3x equals minus 2. Then he did something really clever. He added 9 divided by 4 to both sides. So why on earth 9 on 4? Well, let's just say that the right hand side simplifies to a quarter. Now I just explain why 9 over 4. Notice that the 9 on 4 is actually minus 3 on 2, all squared, and the minus 3 on 2 is a half of the coefficient of x. Now where is all this leading? By choosing minus 3, 1, 2 squared, the left-hand side can be rewritten as x minus 3 on 2 all squared. What the student was doing, in fact, is an application of the following algebraic identity. A plus b squared is a squared plus b ab plus b squared, where a is equal to x and b is equal to minus 3 on 2. This trick of adding 9 on 4 to both sides a few steps back produces this perfect square effect. This technique is called completing the square. Again, it's a very important trick that you're going to see formalized in the next module when we discuss the quadratic formula. What's the whole point of this? Well, notice the last line. We got an expression of the left-hand side with only one instant of x. So now to isolate x is relatively straightforward. Reduce the problem to something similar to what we'd seen before. You just strip away the expression until you get x on its own. So we get x minus 3 on 2. If we take a square root at both sides of the left-hand side, we get x minus 3 on 2. On the right-hand side, we get plus or minus the square root of a quarter, which is plus or minus a half. By adding 3 or 2 to both sides, we isolate x as 3 on 2 plus or minus a half 3 on 2 plus a half is 2. 3 on 2 minus a half is 1. So we get the two answers that we saw previously. I thought I mention that because firstly, it's a precursor to something that we see more the time in the next module, the quadratic formula. But also each want to highlight the fact that even though the student had very little mathematical background, just thinking about imaginatively, just thinking about imaginatively about the numbers and expression involved. He was able to do something really original and creative. I want to emphasize this fact because a lot of you possibly don't have much knowledge about of calculus, but I want you to feel like you are on journey of discovery. Even if you discover something that's well known or even possibly very old or ancient.